Hello class. I wanted to go over the section 4.2 least squares regression line that I was unable to get to, also known as the line of best fit. So for this, we want to find the least squares regression line and use that line to make predictions. So, as you might remember from algebra, geometry, or whichever class, we could connect 2 points with a line. And that's all fine and dandy, right? But a question though that you could ask yourself though is, does a line exist that fits this data better? And when I say fits, right, fit is a very a very strange term in that sense. And the idea of, well, I mean, of course, this data clearly fits this line clearly fits the data. It goes through the 2 points. That's all fine and dandy. But when I say fits the data, that's with regards to these residuals. That's the error or the difference between the observed and predicted values of y. Here in this case, that will be between this data point, the observed value, and the corresponding point on the actual regression line. Notice how there's a difference there. And the line of best fit tries to minimize these residuals. Not just that one, of course, all of them. We have a whole bunch here. 1, 2, 3, 4, 5 others. Though this one appears to be the biggest, maybe almost close to even this one down here. But we have them all over the place, positive and negative. The idea of these residuals, if it is the best fit, the residuals actually add up to be 0. Which then in that case, then you might be wondering to yourself, but doesn't that kind of negate this idea of minimizing them? That's why we can't really use just the residuals themselves. And otherwise, that'll be very boring. This idea was developed by a French mathematician named Adrien-Marie Legendre, and that is this least squares regression line. That line of best fit. So the line y with a little hat on top, so y hat, that minimizes the sum of the squared errors or residuals to the observed value y. In shorthand, that's minimizing the sum of the residuals squared. So before I was saying that if you added up all the residuals, that just makes 0. But if we square them, now that would no longer be 0. And that would be one of the error measurements that we have. And we could calculate that. Mind you, though, the physical hand calculation of it is a little bit on the strenuous side, but we could do that in StatCrunch, as I will show later on. And the regression line is given by this equation here. Y hat is equal to b sub 1 times x plus b sub 0. B sub 1 is the slope of the regression line, so r, the correlation coefficient, times the standard deviation of the y values, divided by the standard deviation of the x values. The y-intercept, b sub 0, is the average of the y values minus the slope times the average of the x values. And as you can tell by this calculation, that can be quite strenuous. And, I've had classes calculate that before. So, I could verify that it can be strenuous. Again, StatCrunch can do that for us. Both of these are rounded to 4 decimal places, unless otherwise specified. Y hat's the predicted value for y at x, and as such, the line always contains the average of x and the average of y. Since the two standard deviations are both positive, the correlation coefficient and the slope are the same sign. Now for an example of doing this, we could find the least squares regression line from this data from section 4.1 on club head speed and distance. But let me throw that into StatCrunch so we could see what's going on here. For this step, we are going to go to Stat, Regression, and then Simple Linear. in this class, we are not going to use either of those other three regression types. Just be aware, though, there are other regression types. We put the club head speed in for x. We put the distance in for y. Everything else here is optional. There is a prediction section here, which we could put in, but it provides other information. I'll show that to you in a moment. But then we hit compute, and we're given a whole bunch of information. Okay, we're given the equation on here with the y-intercept, the slope, the sample size. We have the correlation coefficient on here, the coefficient of determination, estimate of the error standard deviation, and a whole bunch of other information involving those. Estimates of the intercept and the slope, a hypothesis test that we're not going to use, and a whole bunch of analysis of variance table. And on the right here we have the line shown on the scatter plot, which, if you saw that picture before, that directly connected the two of the points. This one here is a little bit off from them in order to minimize that sum of squares residual. So do note that. But on here, though, we do have a regression line, y-intercept of negative 55.7966 and slope of 3.1661, which is where that comes into. Now, in order to do the prediction, we could put 104 in for x. Putting that in here, we get negative 55.7066 plus 3.1661 times 104. That makes about 273.568 yards. If you want an exact value, we could put that even into the prediction part here. Again, though, I did say that it will give us extra information, but we could see the predicted y value here is 286.14237, which mine was a excuse me, did I put 108 in there? That's supposed to be 104. That might be why that's so different. Let me change that. There we go. Gives 273.47797. The one that I did on here was 273.568, but that's just based upon rounding. This one used rounded both beforehand. This one did it without rounding, which is why it's so different. And again, it has all these other parts, but we don't need that for this class. Moving on from that, though, since we have a regression line, we could do a little bit of interpretation involving the slope and y-intercept. The slope can be interpreted, and always can be interpreted. There is never, ever, ever, ever a time the slope cannot be interpreted. It is always interpreted. I can't stress that enough. Always is in capital letters. After all, very important. It can be interpreted as a variation of this. As x changes, so does y on average. If x changes, the expected y changes. And I have down here the interpretation of the slope of that club head speed and distance that we just saw in this last example. That slope was 3.1661. An interpretation of that is something such as, on average, the distance increases by 3.1661 yards for each additional 1 mile per hour in club head speed. Okay? So again, on average, and it always changes the x by 1 in our interpretation of the slope. Okay? But the y-intercept, though, this one is iffy. We have two questions. Is 0 reasonable? And do any observations near x is equal to 0 exist in the data set? Can we have a club head speed of 0? Well, that would be when it is not moving. So I mean, if you look at it that way, potentially. There are no values near 0 on the data set, and if you even were to put a 0 in there, the y-intercept's a negative number. You can't have a negative distance, so we can't interpret that in this case, just the slope. But be aware though, there are times we can indeed interpret the y-intercept. Just so happens not to be this time. For example number 2 here, we could do the least squares regression line again for this data set down here. A graph with the regression line on it, and then this least square, the sum of square residuals for that least squares regression line. And it is displayed in StatCrunch for us, which is always nice. But I kinda need that data first before putting that in here. So let me just copy that on over. And put that into StatCrunch. We're going to go to Stat, Regression, Simple Linear again. And this time we have a label for both x and y as x and y, so I mean those are pretty nice to just put in. Hit compute. Before I get to the line, that second part line, the scatter plot with the regression line on it, if you hit this right arrow, that provides it for us in here. So that's the line. But the actual equation itself is y is equal to negative 2.432 -2.4324 plus 1.6216 x. Hence where this line here came from. Then the sum of squid residuals. That is indeed on here. It is located right here. Where the error source row is and the SS column. 5.0811 that rounds to. That is the sum of the squid residuals. And hence what we requested in part C on here. And that was not what I wanted to do. For example number 3, let's say an engineer wants to determine the weight of a gas-powered car, which will be our x value, affects gas mileage, which will be our y variable, excuse me. The accompanying data represents the weights of various domestic cars and the miles per gallon in the city for the most recent model year. And we first want to find the regression line, treating the weight as the explanatory variable and the miles per gallon as the response variable. In order to do that, we first need to put this data into StatCrunch for us. So let me go and pop that over as well. That being here. And then just paste that into our StatCrunch template. We're going to Stat, Regression, Simple Linear. The weight is our x variable, and the miles per gallon was our y variable, as we wanted. And then we're going to hit compute. So the actual equation for this will be 43.3889 minus 0.0071 x. Okay? So let me fill that in on here. So y hat is equal to 43.3889 minus 0.0071 x. and we could interpret the slope and the y-intercept as appropriate. So for the slope, and let me actually just make this bigger here so I have a little bit more room to work with. But the slope for this, we can interpret this as for every pound added to the car's weight, the gas mileage in the city will decrease by 0.0071 miles per hour on average. And that's the interpretation of the slope. Now the y-intercept. None of these x values are 0. Right? Can a car weigh 0 pounds? No, makes no sense. So because of this, the y-intercept cannot be interpreted. So y-intercept not interpreted. Now, for a certain gas-powered car weighs 3,700 pounds and gets 15 miles per gallon, is the miles per gallon of this car above average or below average for cars of this weight? How do we know this? Well, we could just put in 3,700 into our equation and get this prediction. So we are going to do that y is equal to 43.3889 minus 0.0071 times 3,700. If you do this math out, you get an answer of about 17.1 miles per hour. That's miles per gallon that's supposed to be. I have an hour there, not a gallon. I can very quickly fix that. Miles per gallon. So, because of that, this will be the average. And 15 here now is going to be below average. So, in order to answer this, this would be the miles per gallon of the car is below average, as we just computed. And then this last one, would it be reasonable to use the least squares regression line to predict the miles per gallon of a hybrid gas and electric car? And the answer to that would be a no. Right? As we see here, this is only for a gas-powered car. For a hybrid car, it might be different. So no, they are two different types of car. Two different types of cars. So because of that, it makes no sense to predict that. And that would be section 4.2 there, from what we were doing there in class. Thank you.